Buenos dias. Gracias por estar acá hoy. So today I will speak about metal speciation. Why? Because chemistry is very sensitive to the environment, and particularly for metal complexes, they are very sensitive to the environment in which they are. In the presence of water, so in aqueous media, metals form hydrated ions, and these undergo pH and concentration-dependent chemistry, which might also be influenced by the presence of different metabolites, proteins, and other biological components. I show you here a speciation diagram. I will show you some during this lecture, in which you can see the pH and here the percentage formation relative to the concentration of vanadium, so like a molar fraction of each species. And this diagram is made for millimolar concentration, and you see that for this vanadium-5 species, there are, in a wide range of pH, a lot of species which are present at the same time. For instance, at physiological pH, we can see vanadium in the monomeric form, tetravanadate, divanadate, pentavanadate, and in the lower pH range we have decavanadates. So what happens if we dilute this solution? What do we expect to happen? The monomeric species will become much more important. Okay, so this is the speciation for the same metal at 10 to the minus 5 molar concentration. And now, basically what we have in solution is a species that has monovanadate, so no oligomeric species as in this case. So this tells us that in solution, simply in the presence of water, the type and number of species that form can be very different from each other. Of course, we also have redox active metal ions, and as I told you yesterday, very rarely they exist as free ions in solution or in cells. And so these metals undergo speciation chemistry, which is governed by the pH, the ionic strength, and of course the force of attraction between the metal ion and different biological molecules. And we can see that the oxidation state of a metal greatly affects its toxicity. I show you here two examples. One is arsenic, for which the +3 oxidation state is more toxic than arsenate, so arsenite and arsenate. But for instance, for chromium, it's the opposite. The most toxic oxidation state, it's the higher one. So the oxidation state is very important for its toxicity, and the same happens with, for instance, copper, vanadium, etc. It might also have a strong impact on the absorption of the metal ion, and a classical example is iron 2, which is quite soluble in physiological conditions, and it crosses the membranes through the transporters, and iron 3 basically does not enter the cells and is more prone to hydrolysis in biological systems. So hydrolysis for metal ions is a problem in terms of their speciation in aqueous solutions. Also, and I think we've seen a little bit of this yesterday, copper and iron can catalyze the formation of reactive oxygen species, and therefore the levels of these metal ions free must be tightly controlled, and this is called the homeostasis of the metal ions. And so cells have systems to sense and regulate the concentrations of free metals to maintain it in a non-toxic level, okay? I think we've talked about this. So for instance, here I show you a speciation diagram of iron 3 in the presence of water in a different range of pHs. And you can see that the aqua species, what is considered free Iron 3 is only important in the low pH range, up to pH 2, and then a lot of hydroxides form. There is one question which is quite important in speciation, which deals with lability, because some metals are inert towards substitution and some are labile. But in general, metal species from the third period, so the first transition metal series, are typically labile. This means the ease by which they replace their ligands. As a general rule, we can see that metals with +2 charge are more labile than metals with +3 charge. And this is due to the fact that metal ions are considered Lewis acids, and so they form coordination complexes with the ligands which are Lewis bases. And of course, the electron configuration affects the compound lability, and typically if there are electrons in the higher energy level that we were seeing yesterday, the EG, the compounds are more labile. Okay, so this is the example of copper 2. This is the electron configuration for copper 2. It has 1 unpaired electron, and it is a quite labeled metal ion, while, for instance, vanadium 2+ without electrons here is considered inert towards substitution. In this table, and typically to measure lability, what is done is to evaluate the water exchange and to measure the rate of this substitution. And you can see that, for instance, platinum, both in the +4 or +2, are inert, so they have a low rate of substitution, while, for instance, copper, zinc, iron 2, nickel 2, they are all labile systems, so they exchange their ligands very easily. It is important to keep in mind that lability is a kinetic property and there is no connection with thermodynamic stability. And typically, in real-world systems, we have an intermediate solution, not complete lability and not complete inertness. So I will show you a few systems and some speciation diagrams. How do we get these speciation diagrams? As I've told you, they represent a percentage or mole fractions. You can represent them in both ways, of equilibrium concentrations of different chemical species. These equilibrium concentrations can be computed by solving the mass balance equations for all the species. The problem is that we need to know all the stoichiometry, so we need to propose a model and calculate the stability constants of the ligand species in different protonation states, the metal complexes and its hydrolysis products, and also the ionization constant of water. And then, having all this information, we can model any system, complicated systems. So, if we only have a metal and water, or a proton, okay, I show you here the speciation for zinc, and you can see that zinc, so when we represent zinc 2+ or metal 2+, it means the metal with the hydrated water molecules. And we can see that zinc at physiological pH basically does not form hydroxides. We will have the aqua ion that can be reacted with any ligand, and it has a low solubility product. For copper, we can see that at physiological pH we have mostly hydroxides and a lower solubility product, and for iron 3 is even worse. Okay, so iron is only free until pH 2, copper until pH 7 or 7.5, and the solubility product of iron 3 hydroxides is very, very low. So what if we want to model the interaction of a metal, a proton, and a ligand? So we need to know the constants for the metal. We need to know the protonation constants for the ligand, and as you can imagine, here we'll have the most protonated species, the most basic species, and then we should also measure the interaction of the metals with the ligand, and in the end, this is what we obtain. This is really important because it will tell us which is the species that we will find at physiological pH or at more acidic pH. We can see which is the charge of the complexes, which are not represented there, sorry. And so this is a powerful information about what happens in aqueous solution, okay? And we can take this further and we can model biological systems like, for instance, the blood serum, okay? So a compound to reach a cell typically is ingested or administered through IV, and it will circulate in the body, and this will determine its pharmacological properties. Blood serum is a medium, aqueous medium, pH 7.4, but it has a lot of things in it, like amino acids, different metal ions that might compete for our ligands, low molecular mass ligands like citrates, oxalates, etc., and also numerous high molecular mass components, such as proteins, which I would like to highlight, albumin and transferrin. And all these molecules have potential metal ion ability, and so they might substitute our original ligand. So just to give you an example, so this is the speciation for vanadium now in the +4 oxidation state, okay? In the different pH range, we can see, and this is common for metals, physiological pH, they form hydroxides, which many times are insoluble. So sometimes people ask, did you test, for instance, the cytotoxicity of the free metal? And sometimes we don't do it, some people have done it, but typically the conclusion is that the metal will form an hydroxide which will precipitate from the solution. So in fact, at physiological pH, we typically do not have the free metal ion, okay? So what happens if we have a ligand, like a steel acetonate? We determine the protonation constants of this ligand and study the interaction with vanadium, and now we can see that at physiological pH, what we should have in solution is the complex with 2 steel acetonate molecules and a small percentage of an hydroxide. What we did next was we had the stability constants with albumin, with transferrin, and we modeled what happens when we change the concentration. If we have vanadium and the ligand in these conditions at pH 7 in the presence of 2 micromolar of apotransferrin. Apo means the protein without any metal, and transferrin is an iron transporter. This is the concentration which is relevant in biological conditions in blood, and we could see, so putting everything together, what we are doing here is changing the vanadium concentration. We can see that for low concentrations, like below 10 this is in micromolar, below 10 micromolar, we have vanadium either bound to transferrin, 1 vanadium or 2 vanadiums, or vanadium hydroxide if the concentration of vanadium is higher, okay? So in fact, we do not have either the original compound that we put in solution, vanadium acetylacetonate 2, or for instance, this is the species that could be relevant, when we have vanadium with the two ligands bound to the protein and being transported in blood. So in fact, I would say that if we administer this compound, what we get is the dissociation of the vanadium from the two ligands and the binding of vanadium to transferrin. So in fact, if we see some biological effect, it should be from vanadium alone, okay? So this is the type of studies which is, I believe, are important to do because we need to understand the chemistry of the system in aqueous media and the interaction with biological systems. Of course, what I've been showing you, these speciation diagrams, can be measured simply by mixing a metal and a ligand, changing the pH, and measuring the potential. Okay? And this involves simply protonation states. We cannot do just that. We need to somehow corroborate spectroscopically what happens, okay? And so speciation and solution structural investigations are always done together. And so typically we use the spectroscopy to confirm the speciation that we proposed because we are the ones who suggest a model, okay? Of course, if we want to perform a joint evaluation, we need to have similar conditions in the pH measurements and the spectral data. And this sometimes is not possible because for spectroscopy, sometimes we need low concentrations, like in UV visible, for instance, or fluorescence. And for pHmetry, we need millimolar concentrations. And of course, solubility might also be a problem. So experimentally, there are many things to consider. And we can combine data from different spectroscopic measurements. Okay, so when we measure spectroscopic data, these are structural speciation, while the pHmetry, it's basically a thermodynamic measurement. So sometimes they may not agree. And what happens is when we just use pH potentiometry, maybe we cannot distinguish between different species, like isomers such as FAC, MER, or lambda and delta might not be distinguished. And changes in composition do not always lead to changes in spectra. Having a species which is a monomer or an M2L2 might have the same spectroscopic signature. Or what might happen is that, for instance, if the protonation, the pH processes are happening far from the coordination center, maybe we will not see changes, spectral changes, if we are observing DD bands or, for instance, EPR spectra. I will show you a few examples with different techniques, which I think highlight how powerful these techniques can be. So we can use UV visible spectroscopy. It's one of the most simple techniques. Typically, the compounds follow the Beer-Lambert law. And we can use UV visible spectroscopy to determine the concentration of each individual species. And we can join this with pH data. So what happens is that, and you know this, the UV visible bands are typically broad. So sometimes imagine that we have a major species and a minor species, and sometimes we cannot detect these minor species with accuracy. For instance, this is one system that we were working recently. This speciation is in terms of the ligand because we can make this in terms of the metal, the ligand, the protein, etc. And we can see that we have here at physiological pH, we have a copper ligand 1-to-1 species. We measure this system simply by spectrophotometry. And you can see here the changes, okay, from pH 1.6 until pH 1154. And so basically we follow these changes and we assign and we determine the molar absorptivity spectra for each of the species, okay? And so this is a way to achieve these speciation diagrams. So in fact, in this system, we had 3 different copper complexes in different protonation states, which in fact had very different UV visible spectra. We can also use circular dichroism. When compared to simple UV visible absorption, it's more informative because instead of having just positive bands, these bands might be split and might have positive and negative components. The only problem is that only active species can be detected, optical active species. But we can also see chiral compounds, chiral complexes from non-chiral ligands. The classic example of the ruthenium-2 3 phenanthrene molecules, for which we can have the delta and the lambda isomers. So both of these complexes are optically active and they come from non-optical active ligands. We can use the DD bands, okay, but we need quite high concentrations, which might not be feasible in terms of solubility, for instance, or we can use the ligand to metal or metal to ligand charge transfer bands, and in this case we can use much lower concentrations. We know that the DD bands are forbidden by the Laporte rules, and so they have very low molar absorbance values. So typically they are not sufficiently sensitive. The charge transfer and ligand bands are much more intense, and we can use much lower concentrations, which is always an advantage. The system I've showed you, so we were focusing on the ligand and the ligand to metal charge transfer bands to determine the speciation. I show you here a very simple example. So this is mixing iron 3 with this ligand shown here, and the system is interesting because it changes its color as the pH changes, because different species are being formed and they are shown here. So at low pH we have the aqua iron, okay, shown here as A. Then between pH 2 and 3.4 we have the complex with one ligand, and this solution is blue, okay? As we increase the pH, a second ligand is bound and the solution becomes violet, and between above pH 8 and below 12.7 we have the 1 to 3 metal to ligand complex, which has a different color. So this is like the perfect system when each species has its own color, okay? And of course it was possible to modulate the species, the absorption species, or the absorption spectrum for each of these 3 species, 1 to 1, 1 to 2, and 1 to 3. Above pH 4 we form the hydroxide. So colorful system to study with pH potentiometry and UV visible absorption. We can also use fluorescence. Fluorescence has advantages and advantages. It's a bit like the circular dichroism. It can only be used when the molecules are fluorescent, and it is many times frequently used to determine the protonation constants of ligands, which are fluorescent, but it has several advantages. It is selective, and it can be applied at a more biologically relevant concentration. Because when we use millimolar concentrations, for instance, we can then model it at lower concentrations, which are more biologically relevant, but in spectroscopic terms, millimolar is not a concentration that we find in our body. So with fluorescence, we can lower the concentrations to a more biologically relevant range. There might be a problem, which is if we lower a lot the concentrations, maybe the metal complex dissociates, okay? So the lower the concentration, the higher the possibility of having the complex already dissociated. And so this is something that should be taken care, okay? As I've shown you, the speciation at 3 millimolar is totally different from the speciation at 10 to the minus 5 molar. It is a very good technique when you have a ligand and a complex or complexes with very different fluorescent properties, because then we can use the technique to determine the formation constants. I'll show you an example here, and this can be also important for poorly water-soluble compounds, okay, because then we can use very low concentrations in which solubility might be overcome. So this molecule, 8-hydroxyquinoline, I will speak a lot about it on Friday on my lecture because it's a ligand with which I work. The fluorescence intensity of this ligand is highly enhanced in the presence of metal ions, and particularly gallium-3 or aluminium-3. So this is 8-hydroxyquinoline, the molecule I'm talking about. And what was observed, so these are fluorescence spectra measured as we change the pH. So initially there was an increase in fluorescence, some saturation, and then it decreased. You can see here the data with the pH and the intensity for different ligand to metal ratios, okay? And so with this data, it was possible, so these are the excitation and emission wavelengths that were used, so emission in the visible range, and it was possible to determine the speciation using fluorescence. And you can see that this increase and decrease is due to the formation of the gallium with 3-hydroxyquinoline ligands. It was really nice because these authors, they could use the fluorescence of the complex to study the uptake and distribution inside cells by fluorescence microscopy. So when we have a fluorescent compound, if the fluorescence is in a suitable range that does not interfere with other things in the cell, we can study its uptake and distribution. We can also use NMR, of course. It's also a complementary technique. Typically, what is used is proton and carbon NMR. And we can follow the protonation of the ligands. Of course, protonation occurs at functional groups that typically are not observable in protic solvents or in water, but protonations and the protonations have effects on the chemical shift of the other protons in the molecule, and these are the ones that we can follow to determine the protonation of the ligands. We have systems in which we have fast equilibria, like zinc-2 upon complexation. Zinc is a classical example used in speciation by NMR, but we can also detect, for instance, palladium complexes, because the ligand exchange is very slow. So we have one species in solution that stays as it is. We can also use other nuclei from the ligand, nitrogen 15, oxygen 17, phosphorus 31, and fluor 19. So some of these can be quite expensive techniques if we need special nuclei. But we can also follow the metal, right? Many metals can be studied by NMR, particularly sodium, aluminium, vanadium, but also platinum, scandium, cadmium, etc. For instance, aluminium and vanadium give very simple spectra. You can measure them with high intensity. The bands are broad, but the range is quite wide. But they are not so important as, for instance, iron or copper that do not give you a lot of information, or even platinum. And if we have in solution not only diamagnetic but also paramagnetic species, this complicates the system and hinders the measurement of the nuclear magnetic resonance. Just a very simple example. So these authors were studying this organometallic complex with a parathymine here and this thioalomaltol, and it was possible to confirm the formation of different species, so 1-to-1 metal to ligand or 1-to-2 metal to ligand, because it was possible to follow the different species. For instance, if we have a metal to ligand of 0-to-1, we only have ligand, okay, which is shown here in gray with a peak here. If we have the 1-to-1 complex, it's this one, okay? So in 1-to-1 ratios, we'll have simply the 1-to-1 complex, which corresponds to this peak here. And for instance, when we have 1-to-2, what we should observe are two peaks to the different coordination of the two ligands, which are not equivalent in NMR terms. So NMR is quite powerful to study these diamagnetic complexes. Of course, this study can also be done by changing the pH, if that's what we're interested in. And EPR, for many metals, are paramagnetic, okay? Most of the 3D transition metal ions are paramagnetic. They are not all suitable to be studied by EPR, because typically we focus on simple systems with 1 ampere electron. When we have more than 1 ampere electron, we have different effects. The spectra become more complicated and more difficult to understand. I showed you this yesterday, so high spin, low spin complexes, and we can see that most of the metals have unpaired electrons, okay? And some systems are very good for measuring EPR, such as, for instance, copper-2. Copper-2 has 1 unpaired electron. Okay, I think I'm going backwards. Okay. So the most frequently studied nuclide by EPR are copper, vanadium, iron-3, and manganese. Okay? Copper is the most frequently studied because its spectra are really simple to measure and they are very informative. And in general, copper is a very important metal, not only in biological applications, but also in catalysis and so many other fields. This is a EPR spectrum of a copper species, and I say that it is informative because we have here the splitting into 4 lines, which is related with the magnetic moment of the nuclei. And so different ligands will impose different separations of these 4 lines. This spectra is measured at low temperature, okay? Vanadium is also very easy to measure, but although I love it, it's a much less important metal. So this is the spectrum of vanadium, and you can see there are many lines. They are very informative spectra. So typically what we do is we measure the spectra, we simulate, and we obtain the parameters. And the parameters are the G values and the splitting parameters, the A. And here I show you a spectrum from iron-3, low spin, and here we just have 3 G values. We have no coupling constants, and so iron-3 we can measure, but it doesn't give you a lot of structural information. So I would say that particularly copper and vanadium are very good metals to study by electron paramagnetic resonance. So, as I told you, we can get the spectral parameters, and for vanadium and copper it's very nice because many people have measured the spectra for many compounds for which the structure is known, and there are these correlations. Okay, so this is for copper, it's called the Bloomberg-Paysack plot, and we can correlate the G value with the hyperfine coupling constants, and you have these regions that tell you that if you have copper coordinated with 4 oxygens, its parameters should lie here in this range. For 2 nitrogens, 2 oxygens, it should be here. For sulfur atoms, here. So this can give you an indication of how the molecule, your ligand, is bound to the metal ion. And typically we measure at low temperature, so liquid or helium-nitrogen temperature, because we get the spectra become more informative. Just to show you, this is vanadium EPR measured at 77 Kelvin, so liquid nitrogen temperature, and this is room temperature. The fact that here we just have 8-line splitting, and here we have at least a 16-line splitting, tells you that you can get more information from here than from there. So many times we need to measure at low temperature, particularly also because we are speaking about a change of spin. That's what happens in EPR. The spin of the electron goes from -1/2 to 1/2. And at room temperature, the population of atoms with spin 1/2 and spin -1/2 will be very similar. So the probability for the transition is low. If we decrease the temperature, most of the spins will be in one of the spin states, and we increase the number of molecules that will have this transition spin. Oh, sorry. So can also use mass spectrometry, but the problem is that if we have an inert system, okay, you can use it, but it's a destructive technique, okay, and it can disrupt the equilibrium and speciation in Labelle systems. So it's not the most useful technique in quantitative terms, it's very useful in qualitative terms. So, for instance, SEMS, electrospray ionization mass spectrometry, has been widely used, but it's mostly with gold, platinum, and this type of inert complexes, not much for copper, vanadium, because it will change, the ionization will change the speciation. So just one example, and I think some of you are interested in phenanthrolenes. So these are vanadium phenanthrolene complexes with different substitutions, and this was a paper published in 2000 that identified this BiSH47 dimethyl 110 phenanthrolene, which in fact is this one, as a novel apoptosis inducing anticancer agent. Okay? These authors tested these 10 compounds in 14 human cancer lines. They identified these two as the most potent compounds with IC50 values in the low micromolar range. The bischelated compounds showed better activity than the monochelated compounds, and the cytotoxic activity seems to be determined by the identity of the phenanthrolene, with this one being the best one. And they could confirm that apoptosis was the mode of cell death for these compounds in human cancer cells. So typically when somebody discovers a nice new compound, other people also study it. And so a few years after, almost 20 years after, the group of Peter Lay in Australia decided to evaluate if this cytotoxicity was due to the complex or simply to the ligand. The fact that when you have the 1 to 2 complex, the IC50 decreases considerably might be an indication that the toxicity might be due to the ligands, and also because people have been confirming that phenanthroleins indeed are cytotoxic. But typically, when bound to a metal, they become even more cytotoxic. So these authors, they concluded by doing studies in cell culture medium in the presence of serum proteins like albumin and transferrin. They concluded that the vanadium complexes, which were vanadium 4 easily oxidizes to vanadium 5, and they observed the rapid decomposition in cell culture media, and so they concluded it's not the vanadium 4 complex which is responsible for the cytotoxicity in lung cancer cells. So they also propose that there is oxidation from vanadium 4 to vanadium 5, and then the composition which yields phenanthroline, which then binds endogenous metal ions, copper and iron. And they propose that the cytotoxic activity is not used to the vanadium complex, but in fact to copper and iron complexes that are formed in the cell media. And so they emphasize the need for careful consideration of stability of the different oxidation states of the complexes and what happens in biological media, particularly if we are working with ligands that are active by themselves. So we also studied this system. I will not tell you much about it, but we were concerned with the effect of the presence of bovine serum albumin. So when you dissolve a compound in cell media has a lot of things in its composition. You know, for the cells to grow, they need nutrients, so a lot of amino acids, sugars, etc. And they have to be supplemented with fetal bovine serum. It's a mix of different biological molecules, but it also contains bovine serum albumin. And if you add 10% of FBS, which is the typical amount, you will end up with 40 micromolar of bovine serum albumin, okay? 40 micromolar is a big concentration, particularly when you're studying, when you're trying to determine the dose response curves in which you use concentrations in the micromolar range for your complex. So this is what we try to model. So first we could see that if we mix vanadium 4 with phenanthroline at a 1:2 ratio at pH 7, in fact, we do not have the vanadium with 2 phenanthrolines. What we have in solution is, depending on a concentration, from 10 to 100 micromolar. What we have is mostly vanadium hydroxide, okay? Some vanadium with 2 phenanthrolines, but it's a complex that contains an hydroxyl group, okay? So no vanadium with 2 phenanthrolines in solution. If we mix this with BSA, bovine serum albumin, with 40 micromolar, in the same concentration range, what we will have is vanadium bound to albumin, okay? So in fact, what is uptaken by the cells is a protein with 2 metal ions. You can see here at lower concentrations, we can find vanadium bound to 1 ligand and 1 protein, and a very small amount of this species that was relevant in solution. So in fact, we corroborated the conclusions by the group of Peter Ley that in fact, in solution and in cell media, what we have in solution is not the vanadium complex. It's different species, and whatever effects that we observe are from the ligand alone, because this is a speciation in terms of the metal, but we will have free phenanthroline, but also these species which have the metal in the protein. So I don't know if I have much more time. I can start with the medicinal chemistry. Okay. So what is medicinal chemistry? It's basically the science that deals with the design and discovery of new therapeutical chemicals. And the objective is to development into new useful medicines, drugs. So there are many aspects in medicinal chemistry. I highlight here a few. We might work on the synthesis of new compounds, on the investigation of the relationships between structure and biological activity. This is something I'm quite interested in, elucidating their interactions with receptors. And when I speak about receptors, I mean proteins, enzymes, DNA, the determination of their ADME properties, absorption, distribution, transport, and metabolism, and studies of the metabolic transformations of these chemicals into other chemicals. This last part is a very relevant field, very interesting field, but you need special tools to study metabolism. And typically, mass spectrometry, for instance, is very important. So in this course, I will focus on anti-cancer drugs, so not antimicrobial or antiparasitic, and particularly on the relationship between structure and biological activities, interactions with proteins and DNA, and a little bit on determination of this absorption, transport, and distribution. So chemotherapy. We continue to obtain advances in chemotherapy, although the greatest progress has not been in the discovery of new, more efficient drugs, but mostly at a conceptual level. And what do I mean about this conceptual level? So more effective regimens. Sometimes it doesn't mean developing new drugs, but to understand what happens if we mix different drugs, and the acquisition of knowledge in the mechanisms of action of anti-tumor drugs, which, if we know which is the mechanism of action, we might try to model the design of new compounds to prevent or minimize drug toxicity. And of course, there has been an increase in use of adjuvant chemotherapy. Adjuvant chemotherapy is any treatment that follows the initial treatment. For instance, the designs of drugs to destroy metastases. So this is a big problem, is that after you have a tumor, sometimes after treatment, you will have metastases going through your body that will start new tumors at different sites. And of course, there is an increased knowledge about processes such as the tumor environment, tumor initiation and dissemination, and the growth of metastases. So the advancement has not been in new compounds in the market, unfortunately, but in knowledge about all these aspects which will allow us to develop more efficient compounds. So just one small slide about the history of metals in medicine. This compound that I show here, salvarsan, was developed in the beginning of the last century by Ehrlich, and he prepared many compounds containing arsenates. And this was the one that was highlighted as the best one for the treatment of syphilis. And this was used until the development of penicillin. Then we have cisplatin. I think everybody knows cisplatin. It's a very simple molecule, and I think this is sometimes the beauty, and I think we should focus also on that. Keep the compounds simple, because if we have very complicated molecules, I don't think that's the best way to go. So cisplatin is very simple. Platinum 2 chlorides, 2 amines. And still today, the platinum-based drugs cisplatin, carboplatin, and oxaliplatin that I will show you are widely used and are among the most prominent examples of the use of metals of medicine. In fact, it was after the discovery of cisplatin that people started investing their time in developing metallo drugs, because most of the anti-cancer drugs, besides the platinum-based drugs, are organic compounds that have one target, one protein, and what typically people take are cocktails of drugs that target different systems. So this is I think this is quite common, that approximately 50% of the chemotherapeutic treatments for cancer involve a platinum anti-cancer drug. And so this tells you about their importance and their efficacy, okay? So here I show you first, second, and third generation platinum drugs. Cisplatin, which was marketed in 78, carboplatin in 86, almost 10 years after, and oxaliplatin in 1906, 10 years after. So cisplatin is very effective, but it has several problems that I'm sure you heard. One of them is resistance to treatment, but also systemic toxicity and serious damage to normal tissues. So this is a very simple molecule. I think I have a slide with the mechanism of action, but basically these chloride atoms are substituted by water molecules. It's called the aquation process. First, one water replaces one chloride, then another water replaces the second chloride, and then when platinum finds DNA, it will bind DNA through the nitrogen atoms. This means that it can do it in cancer cells, but it can easily do it with normal cells. And so the systemic toxicity. So people started to invest a lot of time in this field, and the second generation is carboplatin. So instead of having here chlorides, we have this ligand which contains cyclobutane and 2 carboxylic acids, and so it's a chelate, so it's more stable. This means that this compound has a lower aquation rate. It is, I don't know what I want to say. So it is less toxic. It goes more into the cancer cells than into the normal cells. The problem is that it still produces drug resistance during treatment. So the more of this drug that you take, the less effect that you will have, okay? And then 10 years after, oxaliplatin was produced. So now they changed the amine. So we have a chelate on both sides of the molecule. The mechanism of action of the 3 compounds is very similar. They all target DNA, bind DNA, but this one produces less resistance, okay, than cisplatin and carboplatin. So these compounds were very useful in the treatment of many types of cancers, breast, ovaries, colorectal, all kinds of cancers. And in some countries, other drugs were marketed, okay? So you have here the examples of nevaplatin, laboplatin, and metalloplatin. They are mostly used in Asian countries. And it's the same type of strategy. What happens is that, and this is a very important data, only 1% or less of the administered cisplatin binds its biological target, DNA. So the effect, the cytotoxic effect, is produced by binding to DNA and resulting in, so DNA replication doesn't happen and apoptosis leads to cell death. But only 1% goes to DNA. Most of it binds to proteins and low molecular weight biomolecules, especially those containing sulfur, okay, like glutathione and so on. And it is this non-discriminative binding that leads to side effects like nephrotoxicity. Carboplatin, this one has a more tolerable toxicological profile because it has a chelating ligand except instead of 2 chloride ions. And as I said, it has a lower hydration rate and no nephrotoxicity. For cisplatin, there are other advantages, which is the fact that this compound is active against cancer cell lines that cisplatin is resistant to, or that are resistant to cisplatin and carboplatin. So after platinum, people started to develop different metallodrugs, and I think one of the examples, one of the metals that yielded the best results are ruthenium compounds, okay? So the biological activity of ruthenium was recognized in the 50s with a very famous series of compounds, ruthenium polypyridyl that I showed you before, and reports on their anti-cancer activity appeared in the 1960s. And since then, many compounds have been developed because they show significant efficacy against various tumors in vivo, while showing lower toxicity than cisplatin in vitro. I think there is something important with these compounds, that sometimes some researchers that got bad in vitro results, like IC50 values which were quite high, they decided to proceed to in vivo studies, and they concluded that the compounds were great. So sometimes just looking only at IC50 values, so those response curves and determination of the minimum inhibitory concentration, sometimes it's not the best strategy, or aiming to get very low IC50 values might not be the best strategy, because sometimes in vitro and in vivo results are not the same. And if a compound has a very low IC50, it might be very toxic to all kinds of cells, okay? So I show you here some ruthenium complexes that were tested in clinical trials. Up to now, no compound has been marketed, but there is a lot of research in this field. I show you here NAMI-A. This was the first compound to be developed. It's also a very simple compound. KP1019, so these were quite studied, and then people started to make changes in these compounds, and here I show you a compound that I believe has been used for, well, can't remember now. It's also under development. Okay, so again, as is the case with the platinum compounds, the acquisition. So you see that this is wrong. This is not platinum. Gosh. Okay, this should be ruthenium, okay? Ruthenium-3. Okay, so you can see that the metal is surrounded by several chloride ions. These chloride ions typically are replaced by water molecules, just like as it happens with cisplatin. And for NAMI-A, the acquisition is very rapid. This one takes more time, and we want acquisition to happen, but not to be so fast. And an important fact is about 50% of the intracellular ruthenium, which was administered as this compound, KP1019, appears in the nucleus. And if we take into account that only 1% of cisplatin binds to DNA, this is a big percentage if DNA is the target for these compounds, which is not that clear. So you see here 10% of cisplatin accumulates in the nucleus, 1% binds to DNA, 50% in the case of this compound. An a very important series of compounds are, in fact, organometallic ruthenium complexes, called the half-sandwich ruthenium arene, also known as piano stool complexes. And you can see that this is the most prosperous structural moiety for ruthenium. There are many, many people working in this field because the presence of these fragments gives a very high stability to the metal. So the metal will keep this organometallic moiety. And there was a series of compounds known as raptas. I think they also proceeded to clinical studies, which contain this PTA, okay, phosphorus with 3 nitrogens in this cage structure. You can have here simple chlorides, or you can have like chelating moieties, and I think evidence shows that having a chelating ligand is beneficial for the anti-cancer activity. And of course, in this type of compounds, we can very easily change the lipophilicity of the compound, making it more hydrophilic or hydrophobic, which can be important because hydrophilicity is important lipophilicity is important for cellular uptake. So in terms of the mechanisms of action which are known for the ruthenium complexes, there is evidence that these two compounds are able to target both DNA and proteins. So there is not one pathway, and I think this is usually typical for metal complexes, for metallodrugs, that they target different mechanisms of action. And this is a good strategy. So it was observed that after IV administration, this compound could interact with human serum albumin stronger than this one, but both of these compounds are able to bind albumin, which can be a transporter in blood, in a non-covalent manner, so by hydrophobic interactions with the protein. But as I've told you yesterday, albumin transports anything, either coordinated or through intermolecular interactions. There is something very interesting which is valid for these two compounds, but also for other metals, ruthenium drugs, is that typically what we administer, what we prepare are ruthenium-3, and then inside the cell they are reduced to ruthenium-2, which are more reactive. And this reduction occurs with molecules such as glutathione and ascorbic acid. And there are two major mechanisms which are proposed for the action of these ruthenium complexes, which is the activation by reduction, which I've just told you, and the iron mimicking hypothesis. So as you know, ruthenium-3 complexes are more inert. If you remember the graph that I showed you today, so the higher the charge, the more inert the complex will be. And so in solid tumors, it's typical to have a lower pH and lower levels of oxygen. These are called hypoxis systems. And this means that ruthenium-3 will be easily reduced to the more active ruthenium-2. The other thing is that ruthenium belongs to the same group as iron, and we know that elements in the same group share the same properties, and so it is considered that ruthenium is able to mimic iron, okay, in its interaction with biomolecules, for instance with serum transferrin and albumin. And it is also known that tumor cells have a high increase for iron, and so they overexpress these transferrin receptors. And so this might be a way to achieve selective delivery and entry of the metal complexes, although I think people forget that what is being uptaken is not a metal, ion, it's not ruthenium, it's a complex. So the complex needs to be able to bind to the proteins, for instance, transferrin, and not to change so much its conformation that it can still can bind the transferrin receptor and be uptaken into the cell. Okay, now a little bit on copper complexes. I think I haven't spoken much about copper, although I think it's a very interesting metal and one of the, from my experience, and I work with different metals, so sometimes I prepare complexes with vanadium, copper, zinc, iron, etc. Copper is always the most cytotoxic. It's usually the trend. So it's a very important metal because it plays it has a role in a wide range of biological processes, mitochondrial respiration, antioxidant defense, and the synthesis of proteins, DNA, etc. And as I told you for iron, its concentration of the free metal ion is kept at a very low range because it can enter in phantom reactions and produce reactive oxygen species. And so it is tightly controlled, the homeostasis of copper. Typically range as copper 2, but cells cannot uptake it, absorb it. So I'll show you what happens in the homeostasis of copper. The first thing is the reduction of copper 2 by reductases to copper 1, which is then transported inside the cell, uptaken by this copper transporter. It's not specific for copper, it transports iron or any other divalent metal. And you have here a representation of the structure of this controller with copper 1 bound to the cysteine, to the sulfur groups of methionine. So inside the cell, different things happen to copper. There are these chaperones. So this chaperone takes copper into superoxide dismutase, which is a reactive oxygen species detoxifier. It can also bind to this chaperone that can take copper into the nucleus, where it can bind to transcription factors and drive gene expression, or it can be bound in the Golgi network, where production, synthesis of proteins and many other molecules happens. For instance, the synthesis of ceruloplasmin, which is the storer of copper. And then, of course, we have here the mitochondria, where energy is produced, in which copper participates in respiratory electron transport and other redox pathways, and eventually copper will be effluxed from the cell, mediated by copper ATPases. So you see, it's a very complicated process for copper alone. So yesterday we were talking a little bit about the role of copper in cancer, and we can see that this is a topic of study because copper might be involved in the activation of cell proliferation and signaling pathways. There is generally a very high demand for copper when compared to healthy cells, and this has been measured in tumor tissues, and serum also increased copper concentrations from patients with various types of cancer, okay? And there has been an effort to correlate the serum levels, serum copper levels, with the tumor stage, but I think nothing has been clearly established, okay? And I think I've told you today that the angiogenesis, which is the process that involves migration and proliferation of endothelial cells, formation of the vascular system and blood vessels, it's a very important factor in tumor progression, because cells need a high vascular system that brings in the nutrients which are necessary for the rapid growth of the tumor cells. And it is said that copper possesses pro-angiogenic properties. So, in fact, the autoregulation of this copper homeostasis that I showed you in the last slide in tumors, coupled with the important role of copper in the progression of cancer, has led to a great investment in the development of copper complexes for anti-cancer therapy. And so this is, well, while for platinum and ruthenium it's easy to show the highlights, the best compounds, the first generation, etc. For copper, there is a wide range of compounds that have been developed. But basically, we have two strategies. We can either develop chelators, so organic molecules that we administer and which we aim that they will bind to copper inside the cell. And I have here the example of this. This is a molybdate copper complex. And the other is the use of copper ionophores. So molecules that are able to bind copper and transport it inside cells. So increasing the copper concentration intracellularly using what are called copper ionophores. And I show you here some examples. The Bisch-Thiel-Smicker bosons. This is a field of research in which many different compounds have been developed, some with very interesting results. And we also have this molecule, disulfiram. Disulfiram was developed for, I think, for the treatment of alcoholism. I think it's something that it's administered for people that suffer from alcohol addiction. It's in the market, but it can complex copper and form complexes that have very interesting anti-cancer properties. With copper, typically, its biological effect is related with the production of reactive oxygen species and also the inhibition of the proteasome. For instance, this compound, which is shown here, takes copper to the mitochondria, okay, and subsequently increases oxidative stress and causes cell death. Nathan? Yeah, it's okay. Can I go on or should I?
Dejemos la pregunta.
Ah, sí, okay. Bueno, yes. Well, so maybe tomorrow I continue with this, the mechanisms of cell death. This slide is very heavy. I need to work on it a little bit more. But so this is what I wanted to tell you, the importance of knowing what is the active species. So at that pH, what is a relevant compound? It might be the metal, the ligand, or the metal complex. And then I think there have been a lot of efforts in developing different kinds of complexes. And I think we'll go on with these mechanisms tomorrow. Okay? Thank you very much.
Tiempo para preguntas, comentarios. El día jueves podemos retomar con esta parte
Sí.
que quedó.
Sí.
Pueden preguntar en inglés, español, portugués, entre otros idiomas.
Griego.
Griego. ¿Hay alguna pregunta, algún comentario?
Sí, a propósito de lo último, pensando en las terapias anticáncer.
Sí. Sí.
Aquí se ocupó como para el COVID, que es la tecnología de RNA.
Sí.
Si uno puede pensar en inducir la expresión de una proteína, una metaloproteína que pueda regular los niveles.
Sí, sí. El problema es tener solo un targeting. ¿Entiendes?
Pero que las células, tumorales también tienen marcadores y receptores particulares que uno puede
Sí,
usar para...
sí. Y una cosa que se está utilizando mucho ahora es también combinar con inmunoterapia, ¿okay? Que es muy importante, donde en términos de diferentes formas de tratar el cancro, muchas cosas están aconteciendo. No tanto en desarrollo de nuevos compuestos, pero en diferentes formas de atacar el cáncer. Sí, the RNA is also a good target.
Tengo otra pregunta.
Sí.
Sobre la especiación.
Sí.
De esa metodología que tú mostraste,
Sí.
¿hay alguno en que uno pueda seguir el curso temporal de la aparición de las especies?
Sí, siempre. Por ejemplo, yo estaba hablando cuando hablamos de especiación es mucho con pH. Eso es importante porque tienes que pensar, por ejemplo, si administras una droga de forma oral, tienes que pensar que tiene que sobrevivir en el pH del estómago, tiene que pasar el pH del intestino, 6.8, es importante saber lo que acontece con el pH. Pero muchas veces cuando estamos estudiando compuestos, una cosa que hacemos al inicio es ver lo que pasa con el tiempo. Si es estable, stability is very important. Y mismo cuando estás haciendo interacciones con biomoléculas, es muy importante de mirar qué pasa con el tiempo. Si el proceso es muy rápido, si se forma una especie y después otra, porque por ejemplo si utilizares técnicas espectroscópicas, eso te dice qué pasa con el tiempo y si necesitas de esperar mucho, poco. De ahí la importancia de estas cuestiones de inertness and lability, porque para los metales del tercer periodo cambian mucho, ¿no? Todo cambia mucho con el tiempo, con lo que tienes en solución. Son procesos muy complicados, pero yo creo que es muy importante enfocarse en la química, entender lo que pasa en términos químicos, porque eso es la base de todo. ¿Okay?
¿Alguna pregunta?
Mencionó que el cobre se utiliza en la mitocondria con su poder redox para hacer distintas funciones metabólicas.
Sí.
Mi duda es, entonces, de alguna manera podríamos tener como un símil a la cadena transportadora de electrones,
Okay.
pero con como un símil, un igual a la cadena transportadora de electrones, pero utilizando el cobre.
Copper participates in this electron transfer. In the end of the electron transfer, you have some proteins which require copper for its function. So maybe it's a possibility, yes.
O sea, me refería como al uso completo de la cadena.
Más alto.
Que me refería como al uso completo de la cadena, como desde el complejo 1 hasta el 5.
Sí.
De que si es que pudiésemos, porque honestamente no sé si es que ya existe como un complejo que utilicen cobre, pero si es que se pudiese hacer como la cadena completa ocupando solamente cobre.
No te sé responder.
Porque mencionaba que también era como muy citotóxico, entonces, claro, si es que funcionase bien.
Es citotóxica cuando está libre. Eso sí, eso es muy nocivo para la célula si tienes una gran cantidad, porque ahí lo que va a pasar son reacciones que no son controladas. No es como en la mitocondria, que todos los procesos de transferencia electrónica están muy bien regulados. Lo que pasa es que si tienes cobre libre, te vas a formar un montón de especies reactivas que van a iniciar otros procesos. Porque cuando pensamos especies reactivas de oxígeno son malas, no, son moléculas envolvidas en los procesos, son sinalizadoras, etc. Pero cuando es descontrolado, sí. Por eso yo creo que utilizar cobre tiene las cosas buenas y las cosas malas. Porque como vimos, dentro, cobre está en el estado cobre 1. ¿Sí? Lo que administramos es cobre 2. Si conseguimos que el complexo llegue adentro, se va a mantener, se va a reducir. De mi experiencia, si tienes un complexo de cobre 2 y tienes glutationa, por ejemplo, y la concentración de glutationa dentro de la célula es muy grande, como milimolar, que es una cantidad muy, muy grande, el cobre se va a reducir y puede alargar y suciar el ligando, que sigue su camino, y cobre puede impactar los procesos. Pero o ideal, y por eso creo que hay más desarrollo de compuestos de metales más inertes, es que la especie que se forma es la especie que va a entrar, que se mantiene. Con estos complejos de metales que son lábiles y que son endógenos y que el cuerpo sabe lo que hacer con ellos, todo se complica mucho, porque si vas a tener mucho más cobre, puede ser nocivo, no es benéfico normalmente. Y donde ser nocivo en una célula cancerígena es ótimo, ser nocivo también para las células normales es malo. Donde yo no tengo mucho conocimiento de cómo se pasa todo en la mitocondria. Mi conocimiento es siempre un poquito general en relación a la parte celular. Me gustaría saber mucho, mucho más. Por eso no te sé responder directamente a la tua pregunta, ¿entiendes?
Pero así como en general, como está controlado los procesos, sí se podría hacer.
Está controlado. El proceso es muy bien controlado, sí. Hay controladores muy específicos para que todo siga muy, muy bien. Pero la cuestión es esa, si algo que entra en la célula va a tener un efecto en eso, en la homeostasis. Y no solo de cobre. Cobre y hierro tienen cosas en común, ¿no? Es eso.
¿Alguna otra pregunta?
Hello.
Hello.
I have a question. First, you talked about some percentage that 50% of metal drugs are platinum based. I didn't
50% of the treatment, the cytotoxic therapy, the chemotherapy, 50% are platinum drugs.
Okay,
In most hospital settings, so you will receive a cocktails of different types of anti-cancer drugs. Many are just organic molecules, but 50% of the cancers are treated with platinum. So it's part of the chemotherapeutic treatment, which is a lot.
I kind of missed that. I have another question. I noticed you talked about the history for many platinum compounds.
Sorry? I talk about?
The history.
Okay, just a little bit.
Many platinum compounds like cis, carbon, and oxyplatin.
Yeah.
And how any of them can have more toxicity or more damage of tissue, and but I don't know if I missed it or you didn't mention it.
Yeah.
But I'm interested in if there exists any research about any pathways or intracellular factors that can lead to or explain any of those detrimental
Yes. There is, I mean, I think in terms of metal drugs, there is a wide number of research on platinum, cisplatinum, carboplatin, oxaliplatin drugs. So it's like there are many people working on this. What is their mechanism? The mechanism of action is quite fairly known, okay? So it's a simple mechanism. The problem is the mechanisms by which cells acquire resistance to the drug, and also their side effects. And one of the things is this: is that these type of drugs, they bind to anything. This is why I started today speaking about speciation and lability, because it's always the question, you lose some ligands and the metal will bind to other ligands. And for instance, for platinum, the waters are the chlorides are replaced by waters, which are then replaced by any type of biological molecule, and proteins with sulfur groups and different proteins. So there are many pathways by which the platinum drugs acquire resistance. They become much more easily excreted from the cell. Also, this is also a problem. The transporters, the efflux of the compound becomes much more rapid, and I'm sure that there are many studies related with this development of resistance and toxicity. But basically, in a very simple way, you can think that they go everywhere. You know? They go to the cancer cells and they go to the normal cells. Sorry. And if their biological effect is through binding to DNA, they will bind DNA. Sorry. In normal cells.
I don't know exactly how the charge or the oxidation
Yes.
number of any metal ion leads to a different interaction with an enzyme or a protein.
Because we are always looking at the metal as being just the ion, the metal ion. But you never find the metal simply as a free metal. Sorry. It will be coordinated either to water molecules, to hydroxide groups. It's like yesterday I was speaking about phosphates. Phosphorus, OH groups, double O. So, for instance, vanadium-4 will always, if you find it in solution, you will find it coordinated to water, for instance. If it's vanadium-5, a different oxidation state, it forms a species which is very similar to phosphate. And this is the reason why oxidation states, sorry, why metals in different oxidation states have different effects, and many times the effect is due to the phosphate. The fact that for some of them, sorry, this effect from different oxidation states and their toxicity is due to the fact that in some oxidation states, some metals resemble phosphate. And phosphate is very important in any biological process because it's involved in phosphorylation. Many signaling processes involve phosphate. And so if this metal is able to have the same charge at pH, okay, because it's always a question of pH. Because, for instance, phosphate might have one protonation state at physiological pH. Vanillate at that physiological pH is very similar, but maybe arsenate or arsenite will not be, so it is related with these things, okay? And of course, the higher the charge, the higher the interaction with negative charges also. So these things, so it's important to understand that one metal in the +2 oxidation state is not the same as in the +3. It changes a lot of its properties, the coordination numbers, the coordination ability, so it changes a lot of things. We always have more questions than answers.
So Is that what you mean? Some slides before,
Yes.
when you say that the higher the charge of the metal ion leads to some kind of inertness.
Yes, exactly. So typically, compounds with +2 or +1 are more labile, and +3 are more inert. They have a higher charge. This means that they will attract the ligands more, which typically are negative or neutral, with greater strength. So they will stay like that. They would keep it. There are many things that influence it. Like, as I was saying, the distribution of the d electrons, where do the electrons from the ligand go, these type of things. Okay?
Thank you.
Thank you.
Muchas gracias.